Okay, in this video, I'm going to talk about a numerical optimization method called Newton's methods, which is also very commonly used in applying statistical machine learning estimation. So Newton's methods. So it is iterative optimization for iterative is similar to the gradient descent, but it requires the second derivative of the function. For smooth function. Cost function, GW. So usually it's much faster than the gradient descent. Okay. Remember last time we talked about for the linear regression and weighted linear regression we have closed form, but for some of the regressions we do not have the closed form. For example, the logistic regression for classification, we can apply the Newton's methods. So the idea is, I need more space here. Okay, so the idea is, you are standing at a point V. Okay, for example, you're standing at a point V. Okay, you can approximate your cost function near V by a quadratic function. Not like a gradient descent. Gradient descent, we just using the gradient. Actually, you are using the lines to approximate. Here we are using the parabola to tangent at this point V. Okay, and jump to the unique critical value. And then where we go to next step, we go to, instead of going to the learning rate, but here we go to the critical value at this parabola. Okay, so this is, if this is Vt, so this is Vt minus 1. Okay, so that's the first step. Second step, jump to the unique critical value. And then repeat. You repeat 1 and 2 until it converges. So, for example, at the second step, you jump to here, you jump at this point, and then you approximate by the parabola, and then you jump to the critical value. Okay, and then at the new point, you jump to the critical value. So you do not need to worry, not like the gradient descent, you need to assign a learning rate. But here, the learning rate is solved by solving the critical values of the parabola point. Okay, so this plot just shows you the 3 iterations: iteration 1, iteration 2, iteration 3. Okay, we can by repeat this procedure, we can seek the minimum of the blue curve. So this blue curve is our cost function. So each brown curve is a approximated quadratic approximation to the j, and each iteration we jump to the bottom of the parabola, right? And by doing so, we can each step we can learn where our true parameters is, best optimum parameter is. Okay. So this method can be applied to higher dimension too. So for example, for higher dimension, for high dimension, we just solve the Taylor series about V. You learned in your calculus, we learned the Taylor expansion, right? Find Taylor expansion. And we only leave the Taylor expansion with second order. Okay, so in other words, we have the, I think I need more space here. Okay, so you just find in Taylor's expansion, you can find the gradient of your cost function g at w. This w is a point near, let me write down here, point near v. Okay, and gradient at j at v equals to the gradient of v plus so here we need the second derivative, because you need the second term of the polynomial approximation. So the second gradient gv, okay, w minus v, okay, and then plus some higher order term, distance between v and w square. Okay, so this is this second gradient. In the univariate case, is second derivative, but for the multivariate case, you have the Hessian matrix. Of g at v. Maybe let's give you a second derivative one example. Suppose you have your feature space has two features. So you have your v will be v1, v2, right? So the Hessian matrix at the second derivative at v, first derivative is just a vector, right? J at v is just the first derivative, partial derivative with respect to v1, partial derivative with v2. So that's a gradient. Second derivative will be a matrix, because not only you have the derivative with respect to v1, maybe I should write down this. Okay, so you should also have the second derivative of the v1 and v2. Similarly, you should also have the second derivative v2 v1 and second derivative of the v2 square. Okay, so this is just the Hessian matrix. So this gives us the polynomial quadratic approximation, and then by solving this, we can find the critical value. Okay, so this is a gradient, right? And solve the critical value, critical point, W by setting the gradient equal to 0. Okay, so this will give us the iteration steps for the, so we're gonna update this W equals to V, where we're starting our algorithm by subtracting the gradient, the Hessian matrix. You take the inverse G at V. Okay, so this formula is solved by setting this equal to 0. So if you set this equal to 0 and you solve for the W, you solve for W. For example, maybe let me write down here. You let this equal to 0, so you get gradient G at V plus Hessian matrix W minus Hessian matrix V equal to 0. Okay, and then you just minus this side plus this side, both term to the both sides, so you get a second derivative G V W equals to gradient at this is V, sorry, this is V, this is not W, because we need to solve W, not solve V. Okay, so this will be V here. Okay, and times vector V and minus gradient of the GV. And therefore we can solve W equals to inverse multiply this term. Okay, that's how we get this one. That's how we get this one. And then you can this inverse cancel this part, so you get a V, right? Minus gradient Hessian matrix at V inverse times the gradient vector G at V. Okay, so that's how we find the iteration steps for the Newton's methods. So this is the ideas about Newton's methods. So to summarize, you pick a starting point. Okay, so for example, you start with any starting point, W. Okay, and you repeat the steps. You find the second derivative. You solve this term. Okay, and by following this direction, you just so this, if this is W, or this is V, so this is V minus GV inverse times GV. Okay, you get a new point, new one. So we can say the V0, V1, and then we solve V2, okay, and V3, V4, until it finds the minimum, So that's called the Newton's method. But Newton's methods does not know the minimum or maximum or saddle points. So you when you apply the Newton's methods, I think the general idea is once you find the point, you can try to solve the Hessian matrix to see if it's a minimum or maximum. Like you solve the so there's a warning. Does not tell. Doesn't tell. Converge set. Maximum or minimum or saddle point. So the idea is maybe if you pick more initial values. And hopefully some of the initial values can give you a better desired critical point. And if the objective function j is quadratic, Newton's methods needs only one step to find the exact solution. So, for example, if the cost function is like this one, actually by this approximation, you just need one step to. It works perfectly for the Newton's method. Works perfectly if your cost function is the quadratic form. So the closer the quadratic cost function to the quadratic, the faster Newton's methods to converge. Also, the Newton's method is better than the gradient descent for optimization for problems for several reasons. First, the gradient descent, so you do not need advantage of Newton's methods. We didn't pick the step size, right? The step size is determined by the second derivative. Learning rate is determined by gradient of the cost function. Okay. Second, rather than follow the direction to the steepest descent, it tries to choose a better descent direction. It's also second, it choose a better descent, choose better descent direction. Than steepest direction. Okay, So yeah, that's a little bit about a new optimization algorithm. I think in your lab or homework, you will have a chance to practice the Newton's methods.